Okay, so hello everyone. In this session, we will go through the embedding topic, and we will also cover some of the state-of-the-art models that are used to prepare embeddings for our textual data, and why do we need embeddings. So before the first question comes is, what is embedding? Right. So in machine learning and data science, we work with variety of data, both structured and unstructured. And especially when we are working with unstructured data like text or images, then we need to convert this text or image into some numerical format so that it is easier for whatever model that we are preparing for this model to understand it better. So that's why we need some technique that can transform this raw data into some numerical vectors, and this is what the embeddings actually do. So if we talk in terms of natural language processing and machine learning, then an embedding, we can think of it as a mathematical representation of a word or a piece of text that we are processing. And it will be typically in the format of a vector, or you can think of it as a list of numbers. And the purpose of this embedding is to capture the meaning and the underlying context of the text in a way that can be processed by the machine learning model. So the first question that comes to our mind is, why do we even need this embedding? What is the need? We have some very straightforward approaches. We can, the way we process the categorical data. Categorical data refers to some input features that represent one or more discrete items from finite set of choices. So for example, you can think of it in terms of a set of movies a user has watched, or a set of words in a document, or the occupation of a person, etc. So this categorical data is more efficiently represented in terms of sparse vector. Then sparse vectors are nothing but some vectors or tensors which have very few non-zero elements. Most of the values in this sparse vector will be zero. So for example, let's say if we are building a movie recommendation model, we can assign a unique ID to each possible movie and then represent each user by a sparse vector of the movie they have watched. So if we see the image in this screen, right, then each row of the matrix is an example capturing a user's movie viewing history and is represented as a sparse vector, because each user only watches a small fraction of the total all possible movies available. So the last row corresponds to a sparse vector 1, 3, and 6 times 9. This is using the vocabulary indices shown in the above movie icons. Like we can assign a unique ID to each of these movies, and based on that, we can define a sparse vector that will represent the movies that a particular user has watched. So this was in terms of movies. Now, if we are working on text data, then we can represent words, sentences, and documents also as sparse vectors, where each word in the vocabulary plays a role similar to the movies in our recommendation example. Now, in order to use such representations in machine learning system, we need a way to represent each sparse vector as a vector of numbers, so that some underlying information, like what are the similar movies from the list of movies that are available, we can capture these semantic context. But how do we even represent a word as a vector of numbers? So the simplest or the straightforward approach is using one-hot encoding. In one-hot encoding, it is a very common method for representing any categorical data. Here you see the example of animals. We have 5 different animals, and on the right side, you see the one-hot encoded representation. So this is an unsupervised technique that maps a single category to a vector and generates a binary representation. The actual process is very simple. We create a vector with a size equal to the number of categories that are available, and with all the values set to 0. Then we set the value for a particular cell with where the particular category is available. So in the first row, we set the entry for dog as 1, and the rest all other entries will be set to 0. Now, this is very simple approach. A better way of representing this is in terms of bag of words, where instead of representing the data in binary format like 0 or 1, we can represent the count of the category. So let's say we have a text called "a dog in heat needs more than shade." So here we see that some of the words might occur more, and we can represent those words, like we can represent the count instead of one, we can represent the actual count or the frequency of occurrence for that particular word. Now, here is a small code snippet, like how we can use the scikit-learn library to prepare to generate these one-hot encoding vectors, as well as the bag of word vector. So here in scikit-learn, we have a function called count vectorizer. We can use it, and let's say this is the corpus that we have. There are 4 sentences in our corpus, and we fit this vectorizer on our corpus, and then we can get the term frequencies, or we can get the vector representation of each of these sentences. Here in cell number 18, we see the vector representation for each of the words. Now, it represents the frequency of time, frequency of occurrence of a particular word in the sentence. And there is another way of using this count vectorizer. We can set there's a parameter called binary. So if we set this binary parameter to true, then we can use this count vectorizer function to get the one hot encoding. In one hot encoding, we will have the 0 and 1 representation. That's the difference between one hot encoding and the bag of words approach. Another state-of-the-art or a simple approach for generating the vector representation is TF-IDF encoding. So in TF-IDF, we use it is actually a statistical method to find how important a particular word is in a document as compared to all other documents. So TF-IDF lowers the weight of some commonly used words like a, the, is. There are very commonly used words in our documents which may not add more, which may not have more context or information that we can derive from it. So we to eliminate the importance of these words, we can use TF-IDF. So it raises the weight for those rare words which are actually relevant for our analysis. And in term frequency, or in TF, we are giving some scoring for each word or token based on the frequency of that word. And the frequency of a word is dependent on the length of the document. Means in a large size of document, a word occurs more than a small or medium size of document. Now, to overcome this problem, we divide the frequency of a word with the length of the document to normalize it. And by using this technique also, we are creating a sparse matrix with the frequency of every word. Now, in scikit-learn, we have a function for TF-IDF as well. We can use this TF-IDF vectorizer, and we can pass the corpus that we have. And based on the corpus or the training data that we pass, we fit the vectorizer, we get the relevant vector representation for those sentences. Now here you see that earlier we saw the vector representation contain either binary 0 or 1s or the count of numbers. In TF-IDF is a slightly better version of representing vectors. It will indicate some importance as well of what is the importance of a particular word in the entire document. Now, while these models are simple and easy to implement, they do not take into account the relationship between words or their meanings. And this can limit their effectiveness for many natural language processing tasks. In most of the advanced or day-to-day task of natural language processing, we do want to understand what is the dependency between different words in a particular sentence. And since each item is technically equidistant in vector space for all these 3 models, it omits the context around similarity also, like how 2 vectors are similar to each other. So if we talk in terms of the entire vector space, then and if we are using any of these 3 approaches, then all the words in this vector space would be at equal distance from each other. So we can say that hot dog and hamburger are no closer together than hot dog and Pepsi. And as a result, we have no way of evaluating the relationship between any 2 words or entities. We could generate more one-to-one mappings, or even attempt to apply some clustering approaches on the data set and identify the groups and then look into similarities. But it will be an extensive work, and manual labeling annotation is needed, which is kind of not feasible. So intuitively, we want to be able to create a dense representation of these categories and maintain some of the implicit relationship information between items as well. We need a way to reduce the number of categorical variables so we can place items of similar categories closer together. That's exactly what an embedding is. So how actually embedding works? Embedding work by mapping the high dimensional data such as text or images onto a low dimensional vector space. There are a couple of algorithms like PCA that does this dimensionality reduction. That approach can be leveraged here. And the key idea in this transformation is that this low dimensional representation captures the underlying structure and the relationships between the data points. For example, in natural language processing, word embeddings are commonly used to represent words as vectors. Each word is mapped to a vector of fixed length, and usually for our normal day-to-day use cases, this word length, this vector length can range from 50 to 300 dimension. And the vector representation captures the meaning and the context of the word, allowing whatever algorithm that we are using for our analysis to perform better, like the sentiment analysis task or text classification or machine translation or language translation. So there are different ways to generate these embeddings now. It can include some neural network based methods, some probabilistic models, or even graph based techniques are also available. And some popular embedding algorithms include word2vec, GLOW, and FastText for text data. And for image data, we can even train our own convolutional neural network and somewhat of RNN as well. So the first approach or the algorithm that we will be exploring is word2vec. Word embeddings have a capability of capturing semantics and syntactic relationship between words. Word2vec is one such approach that can help us capture all these underlying information or context. Now, every word in a sentence is dependent on another word or other words in the entire sentence. Now, if we want to find similarity and relation between words, we have to capture these dependencies. And word2vec model takes as input a large size of corpus and it produces the output, or it generates the vector representation for the word that we are passing. And this vector space size may be in hundreds of dimensionality. We can define what dimension of vector we want to generate. And each word vector will be placed on this vector. Each word vector will be placed in the entire vector space, and whatever words share similar context or have some dependency among each other will be placed closer to each other. Like if we take the first example of male and female, we see that there is some similarity between woman and queen and man and king. So if you see the color coding for these two groups, then it clearly indicates that woman and queen both fall in the same dimension, whereas the man and king both fall in a different dimension. And coming to the country capital chart, here we see that all the countries and their capitals are placed some very nearby to each other in the entire vector space. And using this word2vec, we can even perform some operations like as shown here: king minus man plus woman is equal to queen. So these type of embeddings are these type of vector space gets generated, and based on these vector space, we can even derive some information by using such simple operations. And word2vec, it internally relies on two approaches. One is continuous bag of words or skip ground. We can, while using word2vec in our while generating the embeddings, we can define which of these two architectures we want to use. And based on our use case, we can select which of these two architecture to use. Now, if we are going for a connected bag of words model, then it predicts the current word based on the surrounding words. As you can see on the left image, we are given surrounding words, and we are able to, we are asked to predict the one missing word. And in skipgram architecture, it's the opposite. We predict the surrounding words based on the current word. So if we want to compare both these architectures, Then connected bag of words is a rather simpler model as compared to skip gram, because in CBOW, we just need to predict that one word which is in focus, and we are given a context of words. And in skip gram, we have to predict more words based on just one single word. So CBOW approach, CBOW model is quite simpler. Also, CBOW is comparatively faster to train than skipgram, as CBOW has to train only on one softmax. Like if we work on any neural network model, and let's say it's a classification task and it's a multi-class classification, then we have to include a softmax layer as in the final layer. And this softmax will calculate the probability for each of the classes. That's what is happening here as well. In CBOW, we are just predicting the softmax for only one particular word. And in skipgram, we need to predict the softmax or probabilities for all the surrounding words. That's why CBOW is comparatively faster to train. Also, if our objective is to identify more frequently occurring words, then CBOW is a better choice, because if a word occurs more often, it will have more training words to train. And skipgram works well when we have a very small data set, and we tend to identify some rare occurring words. Now, we can, there's a library called Gensym. We can use this Gensym library to implement or to take the advantage of word-to-vec model. And yeah, here, this is how we can load there are multiple models available. Like here in this example, I'm using a model which was trained on Google News, and yeah, it generates vector of dimension 300. That's what we can see here. Like in this model, if we pass the word king, then it will generate a vector of dimension 300. And here we see the top or the first 10 numbers that are present in this vector. Now, if we want to identify some similarity, like let's say we want to evaluate this equation, like king minus man plus woman is equal to queen, then that's also possible. In this, we can pass what are the positive words and what are the negative words, and based on that, it will give us a recommendation. Like queen is more relevant to the 60% confidence score, and monarch is relevant with 61% confidence score, and princess is relevant with around 59% confidence score. And if we see we can even get the direct similarity between what is the similarity between women and men. Then we see that it is 76% similar. Then in terms of king and woman, it is just 12% similar, and king and queen, it is 65% similar. So this was all about the word-to-vec approach. Next, what we are going to explore is the glove model. Now, in word-to-vec learns the embeddings by relating target words to their context. However, it ignores whether some context words appear more often than others. For word-to-vec, a frequent co-occurrence of words creates creates more training data. So it does not carry any additional information. But if we just think about it logically, then if we see in our training data, there are few words that are observed to occur simultaneously or together more frequently in terms of bigrams or trigrams, then this context or this information does not have any meaning while working with word-to-vec. But this somehow, while training, this type of information is good to capture. And that's why we need a model that is able to capture this co-occurrence pattern. And glove is exactly the model that does the same thing. It stresses that the frequency of co-occurrence is vital information, and it should not be wasted as just some additional training data. So glove, it builds word embeddings in a way that a combination of word vectors relates directly to the probability of these words co-occurrences in the corpus. Now, the idea behind glove is that the ratios of word-to-word co-occurrence probabilities have the potential of encoding some form of meaning, which can be encoded as vector differences as well. We can use a library called Spacey, and there are a couple of pre-trained models or models available. Here I'm using encode web LG. LG is the large model. There are, based on our use case, we can select a small model or medium sized model, and these models are available in different languages also. Here I have selected EN, that means it's an English model and it's a large model. There are models available for Spanish, German, other languages as well. We can select the model based on our requirement. And here, if we pass this sentence, then this is an example vector representation of spacing, or the glove model that it uses internally. And if we see this, if we calculate the similarity between king and queen using the spacing model, then we see that it is showing a similarity of 72%. Now, if we want to, we can even perform some equations or calculations like king minus man plus woman equals to queen. It is a bit of more complicated as compared to word to vec model, but yeah, we can still do it in glove model as well. So this was all about glove model. The next model or the next approach that we are going to explore is FastText. Now, the idea is very similar to word to vec, but with a minor twist. Here, instead of using words to build word embeddings, FastText goes one level deeper. It uses characters as well, not just words, but characters as well. So in a sense, a word becomes its context. Now, the building stones are therefore characters instead of just the words. And the word embeddings outputted by FastText looks very similar to the ones provided by Word2Vec. However, they are not calculated directly. Instead, they are a combination of lower level embeddings. So if we are working on preparing bigrams or n-grams, like bigrams or trigrams or like that, then in Word2Vec, we just rely only on the words. But in case of FastText, we can even use the underlying characters. Some of the words may have some characters which are similar, like ing extension or suffix that we see in some of the words can give us some more information about, okay, this is some activity or the present tense activity that's going on. So all these intricates can be captured using this FastText model because it uses the character embedding or the character based embedding as well, along with the word. So if we want to explore like how we can implement or use this FastText model, then there is a library called FastText. And there are a couple of models available, like Spacey. We have an option to select which language model we want to use. Here I'm selecting English, and we can load any pre-trained model available. Here again, I'm loading a model which generates vectors of dimension 300. And here you can see that if we pass the word king, then it generates a word vector of dimension 300. And let's say if I'm passing the word king and I want to identify what are the nearest neighbors or the words similar to king in the vector space on which the FastText model was trained, then we see that there are kings, queen, then prince, monarch. These words are available. If we search for Burger King and try to identify the nearest neighbors, then we get McDonald's, Taco Bell, Pizza Hut, and so on. And yep, this is how we can use FastText model. And apart from using the library directly, we can even leverage GenSim library for this as well. In GenSim, they already have an implementation of FastText. So this is how we can use the GenSim library. Now, this was all about word embeddings. Now let's move one step ahead and prepare embeddings for sentences, the entire sentence. So let's say when we are working on individual documents or paragraphs and all, it makes more sense if we prepare sentence embeddings instead of just word embedding, because individual word may not be able to capture more data as compared to capturing information or deriving information from a group of words. And some of the techniques available for in sentence embedding are doc2vec, but ELMo. We will cover all these approaches. So the first and the foremost approach is doc2vec, like word2vec. It is another widely used technique that creates an embedding of a document irrespective of its length. So While word2vec computes a feature vector for a particular word in the corpus, doc2vec computes a feature vector for every document in the corpus. So doc2vec model is based on word2vec with only adding another vector called paragraph ID or document ID to the input. So imagine this is the word vectors. This would be very much similar to, here I'm representing a CBOW example, the CBOW model that we have seen in the previous word2vec approach. So we pass a group of words and the paragraph ID. This is the additional context that we are passing to the model. And like word2vec, in doc2vec also there are two architectures available. One is distributed memory version of paragraph vector, and another is distributed bag of words version of paragraph vector. And both of these are similar to the CBOW and the bag of words approach respectively. So in a distributed memory version of paragraph vector, we predict the next sentence given a set of sentences. And in a distributed bag of words, we just sample some random words from the sentence and make the model predict which sentence it came from. You can think of it as a classification task. And yeah, here in talking about the dimensions we have here. So the input consists of a word vector and the document ID. The word vector is one hot encoded vector, and the dimension would be 1 into V. And the document ID or the paragraph ID has a dimension of 1 into C, where C is the number of total documents in our data set. And the dimension of the weight matrix W will be V cross N, and the dimension for the weight matrix with respect to the paragraph ID would be C cross N. And then we can use any of the operation, like whether we want to average it or concatenate or identify max, min based on the requirement. We can define the operation here. And if we want to implement it, then we first, let's say we have this set of sentences here. So the first and foremost requirement will be to tokenize these sentences. So we use word tokenizer. We will pass all these sentences to this word tokenizer. It will generate the tokens for each of these words. And for doc2vec, we need to even tag these words, like this particular word is coming from which sentence from the entire corpus. So that tagging we can do using the tag document. And this is how the tokens and the tags gets generated when we use this tag document function available in doc2vec library. So once we have prepared the data, then we can just use the doc2vec model as it is. And here we can define for how many epochs we want to run it, then how many window we want to process it, like how many words we want to process simultaneously. That can be identified from this window parameter. Then the vector size indicates the number, the size of the vector that we want to prepare. And yeah, so let's say I have a sentence called I had pizza and pasta, and I want to generate the vector for this particular sentence and identify which of the sentence from my entire sentence corpus is similar or more similar to my query sentence. So I will I will prepare the word tokenization. I'll do the tokenization on this sentence and pass this sentence to the infer vector and then get the most similar part from the model. The model is already been trained on the number of sentences that are present in our corpus. So we can just directly get the similarity score. And here we see that the first sentence, which is I ate dinner, is having around 74% similarity score with I had pizza and pasta. And we had a 3-course meal has around 71% similarity score with this sentence. So this is how we can generate the similarity score. It internally uses cosine similarity. So, or we can even, once we have the vectors, then even we can apply our own similarity function. We can use cosine similarity or Jaccard similarity. Anything is fine. Now, the next approach that we are going to discuss is ELMo. It's a short form for embeddings from language models. Now, if we are using glove representation, then the word bank would be represented by this vector, no matter what the context was. However, it has multiple meanings depending on where it's used. So we need an embedding based on the context it's used in. So to capture both the word meaning in that context as well as other contextual information. So to capture such information or get the context of a particular word, we have a technique called ELMo. So instead of using a fixed embedding for each word, ELMo looks at the entire sentence before assigning each word in it an embedding. Also, it generates character-based embeddings instead of word-based. So the representations are not limited to any predefined vocabulary. And it uses internally bidirectional LSTM trained on a specific task to be able to create those embeddings, so that its language model does not only have a sense of the next word, but also the previous word. That's why we are using the bidirectional LSTM, so that we can get the idea of the previous, we have the idea about the previous words as well as the next words while training the model. And the way we can leverage the ELMo model is using the TensorFlow Hub. In the TensorFlow Hub, there are pre-trained models available here, and different versions are also available. Here I'm using an ELMo model with version 2. And there's a parameter called trainable. We can set it to true or false based on our requirement, whether we want to train this model further or it's not needed. So here is an example of how we can get the embedding for a particular sentence. Now, the first dimension, it represents the number of training samples that we have. In this example, I have only one sentence. So the first dimension, or the first number 1 is just only 1. The second dimension represents the maximum length of the sentence. And here, since I have only one sentence, so it returned me 5. Now, if there are 10 sentences in our training data set, and so the second dimension will represent the maximum length of the length of a maximum sentence, which has maximum length. Yeah. And the third dimension represents the actual vector size or the vector length. And ELMo, it generates vector of length 1024. So that's what it's shown here. And here is a code snippet of how we can generate the embeddings. We first need to load the pre-trained model here, then train if needed, and we pass the similar 6 sentences that we saw earlier, and then we are trying to identify the similarity with a particular sentence, like I had pizza and pasta. So we can use cosine similarity directly on top of this. So let's say we have this sentence and we got the similarity score for each of the corpus sentences that we have. So this was all about the ELMo approach. Next, we have USE, or Universal Sentence Encoder. Now, it is one of the well-performing sentence embedding techniques so far. And the most interesting part in this is that this encoder is based on 2 encoder models, and we can use either of the 2. One of them is the transformer architecture, which is the state-of-the-art model for any NLP use cases. And the another is deep averaging network. Both of these models are capable of taking a word or a sentence as input and generating embeddings for the same. Now, the flow for how USE works is we first need to tokenize the sentence after converting them into lowercase to standardize. Then, depending on the type of encoder, like the transformer or the deep averaging network that we have, the sentence get converted into a fixed dimension vector. So here we define it as the vector dimension as 5 and 2. So it gets converted into a vector of dimension 5 and 2. If we use the transformer, it is similar to the encoder module of the transformer architecture, and it uses the self-attention mechanism. And if we go with the deep averaging network, then it computes the unigram or bigram embeddings first and then averages them to get a single embedding. Then this is then passed to a deep neural network to get a final sentence embedding of dimension 5 and 2. The primary advantage of this network is that the training time is less and almost linear in terms of the length of the input sentence. So here is a high-level diagram of the encoder part of the transformer. We have the input words like or sentence like thinking machine. So we have first do some there's a step for positional encoding. It will capture the position of a particular word in the document. Then we pass the encoded part to a self-attention layer. Based the output of the self-attention layer goes to a layer normalization Then the output of layer normalization goes forward to the feed forward neural network. And then again, we have add norm or residual connection. So in this, I have captured just on a high level what each of these 4 layers mean in terms of this transformer architecture. And here is a deep averaging network. So in deep averaging, what happens? We first create the unigrams like hello world, the bigrams together, hello world, and then prepare an average or calculate average for all these words. And this average is then passed to our entire network. We can define a number of hidden layers, and finally, it will prepare a vector, or it will generate a vector of dimension 5 and 2. And the way we can define or we can implement it is in the TensorFlow hub itself. We have a model called Universal Sentence Encoder version 4. Here, for the example purpose, I'm using the version 4. There are other versions available, and these versions differ based on the training data that has been used to train the models. So we can first load the model, then we pass, let's say here we are passing an example sentence, and this is how we can get the embeddings. So we can just call the embed function and pass the sentence to the model that we have. And if we want to calculate the similarity between any two sentences, then we can just call this similarity measure. I have written a small code how to calculate the similarity here. We pass the two sentences, and it will return the cosine distance between those two sentences. So we can continue with the same example. I had pizza and pasta. This is our query sentence. And here we have some 6 sentences in our corpus. And we can use this USC model to get the similarity for each of these sentences. Now, apart from USC internally uses the transformer as one of the architecture approach, but we can even directly use the transformer architecture. There are some state-of-the-art models like BERT, then GPT that gives better results as compared to the other simpler models, and these models capture the underlying context very well. So this is how we can use the transformer architecture for generating the embeddings. In this example, I'm using the BERT model to get the embeddings. So there's a library called transformer. From the transformer library, we can load the model tokenizer and the model itself. Here I'm using BERT, so I will load the BERT tokenizer and the BERT model. Each of these models have their own respective tokenizer. So we have to make sure that the model that we are using, we also load the similar tokenizer as well. So we can use this command or this code to load any pre-trained models. Multiple models are available based on the training data that have been used to train. We have BERT small, medium, large, case, uncased, different versions available. Here I'm using BERT base uncased. So let's say I passed these sentences. These are what I want to prepare the embeddings, and we will first fetch the tokenizer. We will tokenize these sentences, and for example purpose, I'm just tokenizing the first sentence, and then prepare the token IDs. So how BERT actually tokenizes the sentences is it will first like prepare a list of all the words that are present in the sentence. And then for some of the words, like here we see that it is #DH, #UR, #DRA, like this. So it internally uses word piece model. This model, it creates a fixed length vocabulary of individual characters and some subwords that are present, and generates the tokens. And these hash it indicates that these words or these subwords are part of a larger word. Like if we see ing, then we see that okay, ing is a part of some larger word. If we see at, then yeah, it is part of a larger word, like that. So this is the process that BERT follows. It splits the sentence into token, then it adds special characters, CLS and separator. SCP is for token separator, and CLS indicates the beginning of the sentence. Then it maps the tokens to individual IDs here, and then it will pad or truncate based on the length or dimension that we have defined, and it will use attention mechanism to generate the embeddings. So here is all the steps that we discussed here can be implemented using this encode plus method of the BERT tokenizer. We can pass the maximum length that we want, fed to max length. We can set all these parameters as needed. And this is how we would get the actual token IDs. And yeah, here we load the model. We will train the model based on our, like if needed, we can train the model on our data. Otherwise, we can just go with the normal, the pre-trained models data available. And in this case, we see that there are 13 layers, initial embedding layers, the positional encoding layer that we saw, plus there are 12 BERT layers. The number of batches are 4, the number of tokens generated are 48, and the number of hidden units used are 768. Now it prepares that the dimension would be something like this. Each of this can be represented by, here we have a description of what each of these numbers represent. 13 indicates the number of layers, 4 indicates the number of batches, and so on. And yeah, here I'm just doing some processing, just trying to understand what are the dimensions of the different, when we pass different words. And here is the tokens. And yeah, here we see the distance. Here we see the distance between any two words. So if we want to see the distance for tokens, then it would be somewhere 21, because the distance should be low as possible for any two similar words. And if we see the distance between king to table, then it indicates the distance of 0.73 or 73%. So this is valid, that king and table are not related at all. Yep. And this is another representation. Like there's a library called simple representation, which has implementation of the BERT and other models. This is quite simple in terms of preparing the or fetching the embeddings as compared to the using the transformer library. The advantage of using the transformer library is you get access to some intermediate functions or steps. Like if you want to see the dimensions and explore, work around, play around it, then transformer library is a better approach. If you are just concerned with getting the embeddings and you don't want to look into the intermediate steps, then you can just go for simple representation library. So yeah, it's a simple transformer actually. So we use the simple transformer, we load the model representation model. It's a generic class, and there we can specify which model we want to use, BERT or the model type. The use CUDA is like if you are training it on a GPU or the normal CPU. And yep, that's all. So we pass the sentences and we get the similarity score between these. And if using this sentence transformer or this BERT, if we see what is the similarity score with respect for our query sentence of I had pizza and pasta with respect to the other corpus sentences, then these are the similarity score for the different models that we have. So here is a quick comparison of the similarity scores for the 4 models that we have trained on or used. Just for the example purpose, our query sentence was I had pizza and pasta, and here we see that ELMo is giving better similarity score as compared to BERT for I ate dinner. Likewise, we can get the similarity score for other sentences as well. And one thing to mention here is that one of the reasons why BERT is giving slightly less result, like slightly poor result as compared to ELMo or other models, is because we can use transformers for when we have huge data set, or if there are thousands of sentences, millions of sentences, and these sentences are of bigger length, not just 2-3 words. So in those cases, BERT performs much better as compared to other models. Now, if we do a quick comparison about all the different approaches or techniques that we have used here, then a quick recap of what we discussed here. It goes like this. So GLOW and Word2Vec are both word-based models. That is the model that it takes input as words and it outputs the word embeddings. And both of these are context independent. It does not take into account any underlying context information like semantic or syntactic. Then ELMo, in contrast, is a character-based model which uses the character convolution and can handle any out-of-vocabulary words as well, because it uses character-based approach for generating the embeddings. So it can handle any out-of-vocabulary words as well. It is not restricted to the vocabulary that it has been fed into. Then BERT represents input as subwords and learns embeddings for subwords. Representing input as subwords as opposed to words has become the latest trend because it strikes a balance between character-based and word-based representation. The most important benefit being avoided is the avoidance of out-of-vocabulary error that we usually get when we are training on any fixed length vocabulary. So having a fixed size vocabulary like BERT has a practical advantage of being able to load the vector in a GPU regardless of the corpus size. If the use case that we are working on is quite complicated, we can definitely go with BERT. So, and Word2Vec and GLOW do not take into account word ordering in any of the training process, but ELMo and BERT, it takes into account the word order. Like it understands the positional encoding that we are adding in that we see in the encoder part of the transformer actually does the same thing. It tries to identify the position of a particular word in the sentence, and that's how it identifies or generates the embedding for a particular word. So, yep, I think this was in terms of the comparison. Then embeddings in real world, it can be used in almost all the use cases where we want to process any unstructured data like semantic search, computer vision, recommendation engine, etc. And some of the benefits of using embeddings is it improves our performance, and it reduces the dimensionality, a major benefit, because we reduce the higher dimensional data into a lower dimensional vector space. Then transferability, because embeddings can be transferred to any other related task or domains. So if we have trained our model, or if we have prepared the embeddings on a particular domain, then the same embeddings or vector space can be used for similar domains for other use cases. We don't need to retrain the model again and again. So that's actually a good benefit of embeddings. Then interpretability. Embeddings can be visualized and analyzed to gain insights into the underlying structure and relationships of the data. So I think this was all about embeddings. If there are any questions, any comments, we can discuss on that now. Is it having data in form of hash maps? So Mayank Gupta, you are asking this question. Can you please elaborate which specific model you are talking about here? Can these models be used to embed images and maps? If so, how? So we cannot use these models directly in case of images, because for images, we process the data in a slightly different manner. So we can definitely use the idea and prepare our own neural network model based on convolutional neural network and all. So that's how we can generate the embeddings for image data. Get normalizer takes two positional arguments but 3 1. What's the meaning? Let me check on that. Yeah, so there's an error like get normalizer takes 2 positional arguments but 3 were given. You can definitely refer to the documentation for get normalizer. I'm not sure for which specific model you're talking about here, but you can refer to the method explanation and documentation for this, and it clearly mentions which are the 2 arguments that has to be passed. So for some of these functions, we have predefined arguments. They don't allow keyword key value pair arguments. So that could be the reason why we get this error. What is the meaning of state-of-the-art models? Yeah, state-of-the-art models means models that are more likely used that are in the latest trends right now, and which have applicability for almost all of the use cases. So if we talk about transformers, transformer is one of the state-of-the-art model. Transformer has applicability in many of the NLP related use cases, and now there are some transformer-based models available for image data as well. Vision transformer is one such model. Then another models are available for speech and audio as well. So such type of models are called state-of-the-art models. Fast and fast is considered quite near to each other. So if we are using any embeddings, then embeddings depends on which type of model you are using. So if it's just a simple normal embedding or encoding method that you have used, then based on the Jaccard similarity, we can say that past and fast are almost similar because there is just one letter difference. But if we are using any specific models like we discussed in the webinar, then past and fast would have very less similarity score, or the distance between past and fast would be much larger. What is the scope of electronics and data science in today's industry? In terms of electronics, depends on what type of data we are capturing in terms of electronics, but we can definitely capture some signals available. And if we have some signal data or log information available, then based on that, we can prepare any anomaly detection model, which tends to identify any possible anomaly in the electronic device. And that's one of the use cases for in terms of electronics. Then anomaly detection could be there, then any abnormality if there is any, then some just minor monitoring can also be done in terms of data science. Is the speech or voice encoded the same? Encoding, it could be similar because when we are transforming such audio data into numerical format, it again tries to capture the underlying meaning between the different words that have been spoken. So yeah, I think that's all. We don't have any other questions.